Hello and welcome. In this video we're going to take a look at calculating the mass of a region in space using triple integrals. If you've got a solid in 3D and it's uniform density, then it's pretty easy to calculate the mass. You just calculate the volume and multiply by the density, and that will be the mass. Right? Now we want to look at a little more complicated situation where it's not uniform density, but instead it varies from point to point what the density might be. This is not uncommon in rock formation, for instance, with conglomerates, whatever. You might have different types of material in there that have different density, yet all making up the same rock. You might just have different cooling rates, where the outside, if it's like lava cooling, where the outside might cool first and then to form a shell, and then the inside can either seep out or leave holes in the middle, and so you have maybe less dense inside, and lots of reasons why you might have non-uniform density in an object. Okay. Question is, how do you calculate the mass? Well, the way we're going to do it is not unlike the way we've done a lot of other problems in calculus here when it comes to non-uniform objects. You take your object, you cut it up into a bunch of little pieces. Each little piece, you figure out what it is you want to know. In this case, we want to know the mass of each little piece, and then we add them all up. Right? So in this case, we're cutting them up into small little pieces, small enough that we can assume on that little piece the density is constant, and so we find that volume of that little piece times the density to be the mass of that little piece, and then you do that on all of the little pieces in your object. Again, each little piece may have different density to the other pieces, but within that piece it's constant. Okay. So here's a reasonably simple example. I want to take a cube. I'm going to place it in XYZ space where all X, Y, and Z are between 1 and 2. So between 1 and 2 on the x-axis, between 1 and 2 on the y-axis, and 1 and 2 on the z-axis. Typically, I would place it at the origin or with the center at the origin, but because of the density function I want to use, I don't want the origin involved here, right? That is, the density function I'm going to say is 1 over x times y times z. So the closer to the origin you are, the more dense it is, and the further away, the less dense. Well, it's not exactly that, but bigger x, y's, and z's will make bigger denominators here to make a small density. Notice, of course, you don't want to plug in 0, 0, 0, because then that would be infinitely dense, and that's not practical here for doing these integrals. So anyway, I'm claiming that the mass of this thing is going to be the triple integral here of that density function, dx, dy, dz. That is, the little pieces that I'm chopping them into, the little dv, is dx times dy times dz, and then that little piece gets multiplied by the density, and that's the density function right there, 1 over x, y, z. And so I'm just going to do that triple integral. I do notice that this is I'd say a rectangular region. Everyone's a double integral, but it's a cubical region, right? Constants on all the limits of integration, and I can rewrite this function as a function of x times a function of y times a function of z. That is, it's 1 over x times 1 over y times 1 over z, and I can separate this integral into 3 single integrals and do that. Each one of them is essentially the same. This first one would be the log of x, natural log of x evaluated between 1 and 2. So I plug the 2 in, I plug the 1 in, and I subtract, but this happens 3 times and they're all multiplied together, so hence I'm cubing the whole thing there. And luckily, not luckily, but we happen to know that the natural log of 1 is 0, and so we just get log 2 cubed, which is approximately 0.3330246, etc. Okay. Calculating the mass with non-uniform density. Let's do another example. This one comes from one of the odd problems in the book. No, one of the even problems in the book. And I find it interesting because I think it's poorly worded. this is a solid, is bounded by the cylinder x squared plus y squared equals 4, and the paraboloid z equals 9 minus x squared minus y squared, and the xy plane. Okay, find the mass if the density function is this, essentially the distance away from the z-axis. The further you are away, the more dense it is, and along the z-axis it seems that it's density 0. Okay. Now, the parabola, let's see, what did we have? The paraboloid, z equals 9 minus x squared minus y squared is this thing upside down. The z-intercept here is 9. And it would hit the xy plane in a circle of radius 3, right? If z is equal to 0 here, then you would have x squared plus y squared equals 9, which would be a circle of radius 3. So it's this paraboloid opening downward, just shifted up 9. Okay. Now, the cylinder, x squared plus y squared equals 4. Well, that's, if there was no z, you'd be talking a circle in the xy plane, but since we're in 3 space, this circle is then translated upwards, parallel to the z-axis, and I have it drawn there. And of course, it will intersect that paraboloid here because this is a circle of radius 2 and this is a circle of radius 3, and they will intersect up here somewhere. Okay. Now, the book says the region bounded by those 3 things, the third one being the xy plane. Well, I see 2 parts of space that are bounded by those 3 things, 2 finite ones anyway. There's the stuff inside the cylinder and under the paraboloid, and there's the stuff outside the cylinder under the paraboloid. So this question is just like, which one do they want? It's like, well, let's do both of them and see what the mass is. In fact, it's kind of interesting to me here thinking, I wonder which one actually has more mass, because my intuition is telling me that the volume that's inside the cylinder and under the parabola is bigger than the volume that's outside the cylinder and under the parabola. It just seems like there's more stuff in there. Although that's sometimes misleading because it's a longer distance around the outside than it is around the inside. But I just think that the radius of 2 on the inside is going to have more than the radius of 1, well, the extra of 1 on the outside here. However, it's not just about volume. There's density involved here because the density is increasing as you get further away from the z-axis. So although there may be less volume on the outside here, it's more dense, and that actually may yield more mass, right? It's really very light on the inside. In fact, we mentioned along the z-axis, the density is 0, so there's very no mass on the z-axis and very little close to the z-axis. Okay. The question is, which has more? So we're going to start with the inside the cylinder, and I'm going to do this in cylindrical coordinates. So the couple of things to notice here, the equation of the cylinder would be r squared equals 4, or just r equals 2. The paraboloid would be 9 minus r squared. Okay. And the density function being the square root of x squared plus y squared, the density function is just r. So as I set up the integral now, the density function is just r, and dv, that little bit of volume that I'm going to multiply by here, well, that dv is, so that's r, and then dv is r dz dr d theta, right? That was the cylindrical coordinate, a little bit of area. So density function times a little bit of volume would be a little bit of mass, and the integral now, I have it set up dz dr d theta, so on the inside is the z. Z is running from 0 at the bottom to the paraboloid at the top. Well, the paraboloid was the 9 minus r squared, that's the height. Remember, it's 9 minus x squared minus y squared. So now it's just 9 minus r squared. And then the whole thing is circular. Theta is going from 0 to 2 pi all the way around, and for each one of those, r goes from 0 out to 2. Right? So it looks like that. I can do that inside integral with respect to z. Of course, there's no z's there, so this is just an r squared as a constant with respect to z. So r squared times z would be the integral. Evaluate that between the top and the bottom. So you plug the 9 minus r squared in for z, you plug the 0 in for z and subtract. So I just get this. So I now have a rectangular region integrated with respect to r and theta. The function is easily, well, it's just r's. So it's just, I can split it as 1 times the integral of 1 d theta times the integral of 9r squared minus r to the fourth. That is distributing that r squared in there. And this first one integrates to 2 pi, and the second one here integrates to what? 3r cubed over 5r to the fifth. Plug a 2 in, plug a 0 in, and subtract, and I get a mass of 261.38 something, right? And I didn't give units, so I don't know if this is slugs or kilograms or grams or whatever it is. I mean, it's some unit of mass. Now, let's do the outside of the cylinder. The difference between the inside and the outside is the z value is still bounded above by the paraboloid, 9 minus r squared, and below by the xy plane, z equals 0. It still goes all the way around. Theta goes from 0 to 2 pi, but r is not going from 0 to 2, right? It's not going from here to there. It's going from 2 to 3. So my integral, this is what it was, r was from 0 to 2. Now it will look very similar to the last one, but from 2 to 3. Okay? It's the same density function, the same little bit of volume, r dv, not dv, r dz, dr d theta, and the integral looks the same in the first few steps. It's just that here now, when you are substituting in, you're not substituting 0 to 2, you're substituting 2 to 3, so you plug the 3 in, it's right there, and then you subtract what you get when you plug the 2 in. And somewhat surprising to me is you get substantially less mass here at 92.99, just under 93, where the inside was up there at 2.6 or 261. It's curious to me to ask the question of, where would that, you got a cylinder radius 2, if you could shrink it in a little bit, where would be the half the mass on the inside and half the mass on the outside? I highly doubt that it would be at 1.5. That would be halfway between 0 and 3. Well, no, I haven't figured that out. I haven't taken the time. But there you go. There's a couple of examples of mass given a density function that varies with x, y, and z.